Welcome, physical science students. This is a quick slide video over Newton's laws of motion. We're starting a new unit today, and whether you are home or in class, we need you to know these three laws. You've probably heard of these before. They should sound somewhat familiar to you. I'm going to go through these relatively fast because you'll have access to these slides, and you will also be learning about each of these in class today. This is just kind of an introduction to these laws of motion, okay? So Sir Isaac Newton, he's dead and gone, right? But these laws of motion have stuck around for a very long time. So these are at the basics of motion and forces, what makes things actually move. So let's jump into this. These are the three laws right here. The first law, the second law, and the third law. I'm going to go through and break each of them down for you really quick, but just so you can see all three in the same place. Law one, an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted on by an outside or an unbalanced force. Very wordy, very sciencey. Second law, force equals mass times acceleration. That's just an equation put into words. And the third law, for every action, there's an equal and opposite reaction. Perhaps the easiest one to remember and the most well-known. So let's break these down, okay? The first law, here's the idea. If something is not moving, it's going to stay not moving. That's easy for most people on planet Earth to recognize. But if something is in motion, it's going to stay in motion until something makes it stop. And this is the one that people normally have some trouble accepting, because you can see things sitting here like these pumpkins. They're not going to go anywhere, right? They have inertia. Inertia is related to mass. So the more mass something has, the more inertia it has. That just means if it has a lot of inertia, it's tough to make it change its velocity. So a pumpkin is not just going to start to get up and walk away. It has to be pushed, it has to be pulled or kicked or hit. But once it starts to move, it's going to stay moving unless something makes it stop. And on planet Earth, there's almost always something that makes it stop, right? So that's the tricky part. If something gets hit like a golf ball, it's going to travel through the air. What's going to stop a golf ball? Well, gravity's going to pull it down to the ground. Wind resistance or friction through the air is going to slow it down. And then when it hits the ground as it rolls, it's also going to go ahead and stop eventually. But if you took away all those forces, that golf ball, like in outer space, would just keep going forever and ever and ever. So if there's some unbalanced force, that will make it move. And a force at its basic definition is just a push or a pull. And that's it. No reason to complicate it any more than that. Okay? So why do things on Earth slow down? Well, take a look at this big idea. This is huge. You're going to do a simulation on this in a little bit. Friction causes things to stop. It resists motion. Friction never really makes anything move faster, on the big scale at least. And so we have four types: sliding, rolling, fluid, and static. Okay, sliding friction, of course, two surfaces rubbing against each other. Rolling, a round object that rolls as a relatively low amount of friction, but it does stop it eventually. Fluid, anything moving through an air or liquid. And static friction is this idea that things will stay stopped until it starts to move. Static friction is reserved for things that are not moving. Okay, so if you slide a book across a table, you'll feel friction making it stop. As soon as you stop pushing, friction makes the book stop, right? But if you could get rid of that friction, that book would continue moving, according to Newton's first law, forever until something made it stop. All right, so first law of motion. I guess this isn't going to play. Oh well. If a person is traveling with a car and the car hits a brick wall and stops, the person will continue to move. This is where seatbelts come into play, okay? If you are attached to the car, then you should normally stop when the car stops. But if you're not wearing a seatbelt and the car stops very quickly, you will continue to move forward. And that's Newton's first law. An object in motion will stay in motion unless something makes it stop. So wear your seatbelts, ladies and gentlemen. Here's the second law. Force equals mass times acceleration. Okay? Acceleration is something that we've already talked about and studied last unit. Mass was something that we've studied the entire semester. Force is the new thing here. Okay? The new idea. If a force is applied to something, a push or a pull, that object will start to move. It will start to accelerate. It will change its velocity. But it depends on how big is the force and how big is the mass of the object. Okay? So this idea of net force just suggests that there can be a whole bunch of forces acting on an object, but whoever's winning the push-a-war or the tug-of-war, those forces will determine the direction that an object moves. Okay? I'm going to skip past a lot of this. We'll work through a lot of this in class. Let me show you this real quick. Here are two rocks. Okay? One considerably larger than the other. Gravity is making them both fall, but they're both falling with the same acceleration. The only way that works is if gravity pulls really hard on big objects and not so hard on smaller objects. And that's what makes them fall at the same rate. They have the same acceleration, but their masses are very different, and so the forces acting on them have to be very different. So gravity is pulling on all of us right now. It's pulling on our desks. It's pulling on the cars outside. But depending on the mass of each object, that determines how hard gravity is pulling on it. Okay? So skip that for now. Let's move on to our third law. For every action, there is an equal and opposite reaction. All right? Very commonly quoted. A lot of people have heard of it, but it's very easy to misunderstand, right? So here's the idea. If you're sitting on a chair, you are pushing down on the chair. That's the action, okay? The chair is pushing up on you. That's the reaction, okay? As soon as you get off the chair, and you don't push down on the chair stops pushing up on you, right? Now, if two people jump on a chair, the chair is going to push up on those two people with the same amount of force that the two people are pushing down, right? The chair, its structure, it just pushes up with the same amount of force that is pushing down on it, okay? If either one of those forces was stronger, for example, if the chair pushed up on you harder than you were pushing down on the chair, then you would shoot off the chair. And if you could push on the chair harder than the chair could push on you, then you'd probably break through the chair or break through the floor. But they are equal and opposite, okay? Equal and opposite reaction. So think about this. Fish swimming in the water, their fins or tails push the water backwards, right, as they swim, and that causes the fish to propel forward. That's action-reaction. So the action is pushing backwards on the water, and the reaction is the water pushing forward on the fish. All right. Same thing with a bird flying through the air. The wings push down on the air pushes up on the bird, and that's what allows for birds to fly through the air. So these are all over the place. All of these examples are out there. If a baseball hits a baseball bat, right? The bat pushes on the ball, and the ball pushes on the bat. Equal, but in opposite directions. Okay, so this is Newton's third law, equal and opposite reactions. We see this in rockets all the time. They shoot hot gas out the back or bottom of the rocket, and that causes that gas moving that way to push forward on the rocket or up, and that causes the rocket to move this way. Action, reaction, and that's Newton's third law. Okay, so take those three. We're going to focus a lot on friction next. I'm going to have you do a friction simulation, but you can come back to this video anytime. You're going to have access to the slides, and we will break them down and go through a lot of the nitty-gritty details of those. I wanted to just give you an overview, okay? Please jot down any questions you have, and we'll discuss them in class.